Have you ever wondered why space remains dark despite the sun's blazing presence? It's a question that teases the mind, isn't it? We stand at the heart of a fascinating paradox, the paradox of illumination. Imagine the sun, a colossal, fiery sphere, burning at temperatures of millions of degrees, acting as the central hub of our solar system. It's a gargantuan powerhouse, relentlessly radiating light and heat, enabling life on our humble blue planet. Yet, when we gaze into the depths of space, we're met with a profound, inky void. This paradox is a conundrum that tickles the curiosity of scientists and laymen alike. At the core of this paradox is the sun's role as a source of light and heat. It's the ultimate beacon in our solar system, a ceaseless source of energy. Yet its light doesn't behave as we might intuitively expect. Light, unlike gas, doesn't fill up space. It's not like a balloon inflating in a room, gradually filling every corner. Instead, light travels in straight lines, radiating outwards from its source. Picture a lighthouse on a cliff, its beam slicing through the darkness, visible only when it hits something. A ship, a cliff, a stray seagull. The light from the sun behaves in the same fashion. It rockets out in all directions, but we only see it when it hits something. A planet, a moon, or the tiny dust particles floating in space. So here we are, with a sun that outshines everything else in our solar system, casting light and warmth across vast distances. Yet space, the vast expanse between celestial bodies, remains unlit, a canvas of black velvet studded with distant stars. The paradox of illumination is a riddle wrapped in the mysteries of physics and perception. It's a question that challenges our understanding of light, space, and our place within the cosmos. So the question remains, with such a powerful source of light, why does space appear so incredibly dark? To understand the darkness of space, we must first understand the journey of a photon, a particle of light. A photon is a fascinating little bundle of energy. It's the smallest measurable unit of light, born in the fiery heart of our sun. Imagine it embarking on an epic journey, a cosmic voyage that begins deep within the sun's nuclear furnace. Here, through a process called nuclear fusion, hydrogen atoms collide, creating helium and releasing energy in the form of photons. Now, this newly birthed photon doesn't just zip right out of the sun. Oh no, it faces a dense, energetic crowd of atomic particles. The photon bounces around, absorbed and re-emitted by atoms in a frenzied cosmic dance. This process, called the random walk, can take a staggering 100,000 years for a photon to finally reach the sun's surface and begin its journey proper into the cosmos. And how fast does our little photon travel, you may wonder? Well, it zips along at the speed of light, a blistering 186,000 miles per second. That's fast enough to go around the Earth 7.5 times in just 1 second. Now, photons, being particles of light, travel in straight lines, unless they're acted upon by other forces like gravity. But space is vast and mostly empty, so our photon often has an uninterrupted path. However, remember that space isn't just a void, it's filled with galaxies, stars, planets, and even stray particles of dust. Yet these objects only take up a tiny fraction of the universe. The rest? Well, it's just emptiness. So our photon, even at its blistering speed, can only light up the objects it directly hits. Everything else remains in shadow, unseen and untouched by the photon's journey. Therefore, vast stretches of space remain dark because they are not in the direct path of photons. And that, dear listeners, is a glimpse into the paradoxical journey of light in our vast, dark cosmos. Now let's take into account the role of distance in our paradox. When we gaze at the night sky, we're peering into a vast expanse that's mind-bogglingly huge. We're talking about distances that leave our familiar earthly measurements in the dust. Kilometers, miles, they're just not up to the task. Instead, we use light years. The distance light travels in a year, which is about 6 trillion miles or 9.5 trillion kilometers. Now, the sun, our neighborhood star, is a mere 8 light minutes away. That means it takes light about 8 minutes to reach us from the sun. Despite this relatively short distance, the sun's light is already significantly diluted by the time it reaches us. Imagine how much more diluted it must be at distances of light years. Now, why does the light dilute? Well, let's introduce a nifty bit of physics called the inverse square law. This law explains how the intensity of light decreases with increasing distance from its source. Simply put, if you double the distance from a light source, the intensity of the light is reduced to 1/4 of its original intensity. So, Picture a lighthouse. Up close, its light might be blinding, but as a ship sails away, the light becomes less and less intense, until at great distances, it's just a pinprick in the darkness. The same principle applies to the sun and its light. The immense distances in space mean that the light from stars gets spread out over an increasing area, which results in a decrease in the intensity of the light. This spreading out of light over vast distances is one of the reasons why space appears dark to us despite the presence of countless stars. So the immense distances in space significantly dilate the sun's light, contributing to the darkness we perceive. This is an integral piece of our paradox puzzle, but we're not done yet. There's more to this story, and we'll delve deeper in our next scene. Stay tuned. But what about our perception? How does that factor into the darkness of space? Now that we've understood the paradox of illumination, the journey of light and the role of distance, it's time to delve into the realm of human perception and its role in the darkness of space. Light and darkness, as we perceive them, are not simply about the presence or absence of light. They're about how our eyes adjust to the amount of light available. Our eyes, you see, are marvelous little organs. They are designed to adapt to a wide range of light levels. This ingenious ability is what allows us to see in the bright light of a sunny day and the soft glow of a dimly lit room. Now imagine you're floating in space, away from the Earth and its brightly lit surface. You're surrounded by the vast expanse of the cosmos with the sun behind you. Your eyes would naturally adjust to the lower light levels of the stars and distant galaxies. As a result, the space around you would appear darker despite the sun's light streaming all around. This phenomenon is a bit like being in a brightly lit room and looking out a window into the night. Even though there's plenty of light in the room, the world outside the window appears dark. This is because your eyes have adjusted to the bright light inside, making the less illuminated outside world seem darker in comparison. Similarly, when we gaze into the cosmos from our brightly lit planet, or when astronauts look away from the sun or the Earth in space, it appears darker. This is not because space is devoid of light, but because our eyes have adjusted to the brighter light sources. So the darkness of space is not just about the distance light travels or the lack of objects for it to bounce off. It's also about how our eyes perceive light and darkness. Even with the sun's light streaming through space, our eyes perceive it as dark when we look away from direct sources of light. So we've taken a journey through space, light, and perception. Let's piece it all together. In the grand theater of the universe, the paradox of illumination sets the stage. It's a curious question, isn't it? How can the sun, a colossal ball of burning brilliance, be so far away, and yet the vast expanse of space remains shrouded in darkness? The answer lies not in the absence of light, but in the way we perceive it. We embarked on this journey by understanding light itself. Light, as we've learned, is not just a mere illuminator. It's a cosmic courier carrying information from the farthest reaches of the universe to our very eyes. But remember, it's not omnipresent. Its presence is dictated by the paths it takes, the objects it interacts with, and the eyes that perceive it. Next, we delved into the role of distance. Space, like the silence between musical notes, plays a crucial role in the symphony of the cosmos. The sun may be our nearest star, but its light takes about 8 minutes to reach us, a testament to the vast expanses that lie between us and our solar companion. More importantly, the vast majority of stars are so far away that their light, while existent, is not intense enough to light up our night sky. Then we explored the perception of darkness. Our eyes, incredible as they are, have their limits. They are tuned to perceive light in certain ways under certain conditions. The sparse starlight dispersed across the cosmic canvas falls below our threshold of perception, rendering space as darkness in our eyes. And there you have it, a simple explanation for the seemingly complex paradox of why space is dark, despite the sun's blazing presence. A testament to the vast and intricate nature of our cosmos.